Alright, so we left off with our last set of videos last week talking about graded potentials, EPSPs, IPSPs, whether they are respectively depolarizing graded potentials or hyperpolarizing graded potentials. So make sure that you review that before we move on so that you can understand where we're going, because we're going to build on that. So what we have going on, once we have a depolarizing graded potential or an EPSP that is strong enough to reach the initial segment of the axon and depolarize it to the threshold, which is about negative 60 millivolts. So that's going to trigger those voltage-gated sodium channels to open at the initial segment of the axon, and we'll have an action potential. And this is what it looks like if you were to graph the action potential, with this as the millivolts and then this axis as the time. So keep in mind that this whole thing is happening at just one small segment of the axon, so just one voltage-gated channel area, if you will. And then it's going to happen again and again throughout the axon. So we're just thinking of just one small spot in the axon, what's happening to that one tiny spot in a particular period of time. And it's a very brief period of time because this is an electrical activity, so it's not going to be very long at all. So let's walk through this. So let me zoom out a little bit so you can see that. Okay, so we have our EPSP, or our depolarizing graded potential, and that will depolarize our membrane to threshold about negative 60 millivolts. So I should put that there, negative 60 millivolts, and that's from our resting, which was negative 70 millivolts. So once we reach negative 60 millivolts, this is going to happen. We're going to open our voltage-gated sodium channels because we reached threshold. When we do that, we know that sodium wants to go into the cell, so sodium's going to go into the cell and we're going to depolarize, getting more and more positive. This could get up to about positive 30 millivolts, so that's a pretty steep depolarization. Now when we hit about positive 30 millivolts, that's number 2 here, that's the peak of our action potential. And these two things are going to happen. One, the voltage-gated sodium channels close. So if you remember, with our voltage-gated sodium channels, we had activation gates and inactivation gates. So here, for number 1, we open them. For number 2, we're going to still have that activation gate open, but we're going to close the inactivation gate. And remember, we went over the structure on one of our previous videos of how this works. So we're close the inner door here for number 2. At the same time that we do that, we open our voltage-gated potassium channels. So let's think about what happens here. When we close the voltage-gated sodium channels, sodium can't come in anymore, so we're not going to depolarize anymore. And then at the same time, we're opening these voltage-gated potassium channels, and we know that potassium wants to leave the cell, so out goes potassium. With it, it takes its positive charge, so it's going to get more negative inside the cell. So we repolarize the cell. Okay, so that's that slope here, going back down again. Now, as we get back down to approaching resting membrane potential, we're going to return to normal permeability. What that means is that we close our voltage-gated potassium channels. Now, these are what are called slow channels. They don't close all that fast. I mean, it's still a fraction of a second, but it's not as fast as sodium channels. Sodium channels are called fast channels because they open really fast, they close really fast. With potassium, they're going to just take a little bit extra time to close, and that's going to become important in our next step. So just keep that in the back of your mind. But as we return to normal permeability, these potassium channels are closing. The voltage-gated sodium channels are just going back to normal resting configuration. So if we think of the sodium channel, we let the inactivation gate drop open again, and then the activation gate is closed. So sodium can't come in, but we could open this again if we wanted to. When it's like this, we cannot open it again. So we're just back to our general resting configuration with our channels. Closed, but able to open if they wanted to. Now back to that slowness of the potassium channels. Because they're kind of slow to close, we end up with a situation where potassium overshoots the resting membrane potential because it's able to kind of sneak out. A little extra potassiums are able to sneak out, bringing that positive charge with them, so leaving a bit of negativity behind. And it can get it down to negative 90 millivolts. And at that point, the potassium channels, not only are they closed by the time you reach here, number 4, but also this should look familiar to you as the Nernst potential for potassium. At that point, even if those channels were open, potassium is not going to leave anymore. It's going to be at its equilibrium. So we call this the hyperpolarization period because it's, here's resting, say. So we're below resting. We're hyperpolarized, super polarized. So we're extra negative. Then the action of the sodium-potassium pump, plus just general leak channels, everything trying to get back into your resting potential will carry you back up to your resting potential. Now, 2 more things to add in about this action potential. From here to here, this is where our voltage-gated sodium channels have that inactivation gate closed. So you cannot open this channel again during this time because that inactivation gate just will not open again. So here, you cannot have another action potential. You cannot re-stimulate the cell while it is here. And this is called the absolute refractory period. You absolutely cannot have another action potential at this part of the axon here. Now, when you get to normal permeability, then you're like this. You could open those sodium channels again and start another action potential, but you're also hyperpolarized, so it's going to be that much harder. Because instead of just going from negative 70 to negative 60 to open those voltage-gated sodium channels, you're going from negative 90 to negative 60. So you have this extra 20 millivolts of stimulus that you would need to have in order to have another action potential. So this is more difficult. And that is called the relative refractory period. Okay, now remember that this is just one part of the axon. So if we were to say, look here, this is happening here. When that happens there, let's get a different color so you can see. We're going to have our sodium coming into the cell and diffusing in all directions because of this. The sodium channels are open, sodium's coming into the cell. So we get this little graded potential going on here. And that should be enough, or will be enough, to open this next set of voltage-gated channels. Then that set goes through this. Sodium comes in, diffuses in both directions, opens the next set, and that set goes through this. So that will be happening all the way down the axon, or if we had myelinated it, it would be kind of skipping its way down the axon. But at each segment that it's happening, all of that will be happening at that segment. Now you might be wondering, okay, why doesn't it move backwards, or what we would say in a retrograde direction? Why doesn't that action potential just keep kind of bouncing back and forth up and down the axon? And the reason for that is the absolute refractory period. So let's do the middle one. While the middle one is at the peak of its depolarization, so when the sodium is coming in and diffusing in both directions, this set of channels is in the, oops, we can't see where I'm going, over here. So it's in the normal permeability state. So we can open our voltage-gated sodium channels. But the ones in front, so this one, while this middle one is at the peak of its action potential and the sodium's diffusing in all directions, this one is in its absolute refractory period. So even though sodium is coming in and trying to depolarize the cell there, it will not open these voltage-gated sodium channels because they are closed. Okay, so what happens here then? Just to summarize everything that we've done and then get down to neurotransmitter release in the end here. We have our EPSP, our depolarizing graded potential. In the case of neurons, caused by usually opening sodium channels. In other situations, it could be caused by opening calcium channels because calcium will also come into the cell and it also is a positive ion. Either way, we have our EPSP. It's strong enough to reach threshold at the initial segment of the axon and then trigger that action potential. So we have the action potential, the action potential, the action potential, all the way down till we reach the synaptic knobs where we have neurotransmitter found there. And that neurotransmitter will be found in